In part 2 of our torques and moments of force chapter, we're going to focus on the maintaining equilibrium component of the chapter, as well as center of gravity and how your base of support can actually have a large influence on force applied. So in the state of static equilibrium, all external forces must sum to zero. So external torques about any axis must sum to zero. Therefore, our sum F and sum T have to equal zero for a component or body to be in a state of static equilibrium. Now, net torque can be calculated by summing torques in opposite directions. So torques around the same axis can be added and subtracted. So if you think about this in a mathematical or quantitative manner, the sum of torque, or our net torque, is going to be calculated by adding the torque in clockwise direction with the torque in the counterclockwise direction. So the sum of the torques acting to rotate in one direction are offset by the sum of torques acting to rotate in the opposite direction. In looking at this free body diagram of a ruler with pennies situated on both sides of our axis of rotation here in the middle, we can see that this is actually providing a state of static equilibrium, because the force of these two pennies on the right are going to cause the ruler to go in a counterclockwise manner, a clockwise manner, whereas the force of the penny here on the left would cause the ruler to rotate in a counterclockwise manner. So when we sum these two torques that are going in opposite directions, we have to look at the moment arms here. So one penny on the right side has a moment arm of 2 inches, one has a moment arm of 3. However, the penny on the left has a moment arm of 5. So even though the force on the right side is greater than that on the left, the moment arm is actually going to offset the difference in the forces being produced downward, such that the sum of the torques is actually going to equal 0. Using an anatomical example of holding a 20-pound dumbbell in your hand with the elbow at 90 degrees, and your aim is to produce a equilibrium or a state of static equilibrium as you're holding the dumbbell. So if this is your humerus, here's your elbow, here's your forearm, here is the dumbbell, right? Obviously, to create a state of static equilibrium, our muscles are going to have to provide equal and opposite force, right? So if the dumbbell is providing a force downward, then our muscles are going to have to provide equal and opposite in the positive y direction. So the first thing that we can do, if we know that these net forces have to sum to 0, is we can calculate the torque of the dumbbell. So without converting these units to metric system, we can calculate torque with T equals F times R. So in this case, T is going to equal negative 20 times negative 12, because our 20 pounds is equal to our force, and our 12 inches is equal to our moment arm, or variable R. So in this case, the torque of the dumbbell is going to be equal to, this should be negative 240 pounds, or pound inches. So to determine how much force is produced by our muscles, or the muscles that are surrounding the elbow joint, right? Again, we need a net torque of 0. So essentially we're going to take the torque of the dumbbell and add the muscle torque and set this equation equal to 0. So the sum of F times R is going to be negative 20 times negative 12 plus our muscle force times negative 1 inch. And the reason that this is negative 1 inch is because we are approximating that, again, here is our dumbbell, here is our elbow, this is our forearm, this is our humerus. We are approximating that the attachment site of the bicep, which is the muscle that is going to maintain this static equilibrium because it is a muscle or an elbow flexor, right? So we are approximating that the attachment site of the bicep is approximately 1 inch away from our axis of rotation or the center of our elbow joint, okay? So using this equation, we will algebraically move this to the other side. We will get F sub m times negative 1 is equal to negative 20, negative times 20 pounds times 12 inches, and then we will end up with a muscle force of 240 pounds. So moving on to center of gravity, this is the point in a body or a system where the entire mass may be assumed to be concentrated. So CG is the variable that will represent center of gravity. It is an imaginary point in space. It is not a physical entity, and it's certainly not a fixed point. So our center of gravity, especially in human motion, changes constantly when parts of an object or parts of our body change position. So our force of gravity acts downward through the CG. So if we think of our trunk as basically a box, right? Typically, our center of gravity is approximately right in the middle of our trunk, acting downward. Now, one thing that needs to be expressed is that females typically house their center of gravity a tiny bit lower than men because our weight is usually more distributed in the pelvic and abdominal area, where men or males typically have their weight distributed up in their upper extremities, specifically their chest and their upper back and their arms. So the center of gravity, in locating this, it is the point of balance. So with the human body, we have 2 hands, 2 forearms, 2 upper arms, feet, shank, thighs, 1 trunk, 1 neck, and 1 head. So to determine where our center of gravity is, it is the point around which the entire system or the net torque of all of our body parts is equal to 0. So depending on your weight distribution, depending on the way you stand, depending on several factors within your body, this can change your point of balance or change the exact location of your center of gravity during any given movement. So in determining center of gravity from a mathematical perspective, it is going to equal net torque is going to equal the sum of the weight of one element times the moment arm of an element, and is going to be equal to the sum of the total weight of the object times the moment arm of the weight of that object. So the RCG here is the location of the center of gravity of the object relative to the axis about which the moments of force are measured. So in this example, we will use a barbell in which someone, and this is in your textbook as well, but in which someone has put 20 kilogram plate on this end, a 15 kilogram plate on the other end, and then the barbell itself is 20 kilograms. So in this scenario, we are going to create our axis of rotation here to determine where the center of gravity is of this barbell. So to mathematically determine the center of gravity, we have to take the net torque, or the sum of all of these torques based on the moment arm that we created from the axis of rotation, and the weight of each of these 3 points. So the weight of point 1 is going to be equal to 20 kilograms times the moment arm, which is 0.4 meters. The weight of, the torque of point 2 is going to be the other weight plate times the moment arm, which is 1.8 meters. And then the other is the center of the bar. The bar is 20 kilograms times 1.1 meters from the axis of rotation. So in this scenario, we would be using weight of each of these points, but mathematically we can determine that weight is going to be equal to mg, right? So algebraically, we can then rearrange it to where the mass and the moment arm are summed together and then multiplied times gravity itself. So to determine the net torque, we get G times 57 kilogram meters. Then we are going to equate the G times 57 kilogram meters to the moment of the total weight of the system, and then solve for the center of gravity moment. So this will be the net torque is equal to total weight times the center of gravity moment arm, and be set to equal the gravity times 57 kilogram meters. So we get gravity times 57 kilograms, which is the sum of the masses. So 20 plus 20 plus 15 is going to be 55. Okay, so that's the total sum of masses of each component, multiplied by the center of gravity moment arm, and then equal to the G times 57 kilograms. So mathematically, we would then get 57 divided by 55 by moving this over, and our center of gravity moment arm is going to be equal to 1.04 meters. So our center of gravity would then be 1.04 meters away from that axis of rotation that we determined on the right side of the barbell. So in determining center of gravity of the human body, our center of gravity location depends on the position of each limb. So typically with females, our center of gravity is 55% of our standing height, whereas with males it is 57%. Therefore, it is a little higher, as I discussed in a previous slide. Now, if you lift your left arm away from your side, then your center of gravity is going to shift left. If you lift your left arm in front of your body, then your center of gravity is going to shift forward. If you raise both arms away from your side, your center of gravity would then shift upward. So this is just a description of what we talked about in a previous slide, where the position or change in position of any of our body segments can and will change the direct position of our center of gravity. So this is just a depiction of our center of gravity placement relative to the human body height in anatomical position. So in males, it is going to be a little bit higher than in females. Again, males is typically 57% height, where females is typically 55% height. Relative to center of gravity and performance, when a body is a projectile, so it's moving through the air, our center of gravity actually follows a fixed parabolic path. So if you think about a gymnast or a swimmer or a diver, or even a track athlete kind of going through the air, our body segments rotate around a fixed path of the center of gravity. Okay, so our center of gravity is going to move in a fixed parabolic path, while our segments are actually rotating around this center of gravity path through the air, whether you're doing some type of flip or a dive into the water. You are going to rotate about your center of gravity regardless of what you're doing in the air. Now this is a good depiction of how center of gravity height can actually be fairly similar across different performance, or in this case jump techniques, but the overall result of the jump in these three cases can be fairly different. So if we look at this first technique of having just one arm up, she's going to reach a higher height, or a greater height compared to the others. With two arms up, her center of gravity is actually higher on her trunk, but relative to the ground, it's really not changing much at all, and her jump performance height reduces slightly. And then again, if she raises her legs and her arms, her center of gravity is going to be even higher on her trunk, but again, relatively the same compared to, or relative to the ground, and her jump height is actually even lower. So sometimes with performance especially, the location of our center of gravity is going to change within our body based on techniques that we are using, but may not change much at all relative to a fixed point like the ground, but can actually render pretty significant differences in overall performance outcomes. So moving on to stability relative to our center of gravity. Stability is the capacity of a body to return to equilibrium when it is displaced. So our stability is not easily moved or thrown off balance. Factors that affect stability are the height of center of gravity, the size of our base of support, and the weight of an object. So a lower, wider, and heavier object or person is going to be more stable. So our stability based on our base of support can be looked at by surface area of our base of support. So if you see this lineman or this running back, his 3-point stance, his surface area is relatively good. He's pretty low to the ground. So he would have a pretty nice stable base of support. The next example would be a little bit better because our surface area is even wider, and she is again low to the ground, so the height is good, the width is wide, so we are good on the characteristics there. Now moving on to our examples on the right, these surface areas are not as large, so our stability, or based on our base of support, would of course be lower. Continuing to these last examples, these are going to be even less stable than the conditions on the previous slide. So if you look again at our surface area, this ballet dancer is obviously going to have the lowest stability based on her base of support, because the surface area is basically the surface area of her toe. So if you look at the other athletes, they have a decent base of support, but they're not very low to the ground, so their stability would then be decreased. So that is all we have for part 2 of our chapter 5 lecture.